Thank you, Craig. I'm going to focus on just a small area. It touches on some of the things that Tony in particular was talking about in the water savings area. So I'm going to talk about water savings from investments in infrastructure. Now, I'm not really going to talk about the economics of this. There's been quite a bit of comment on by Productivity Commission and others about infrastructure improvements as being likely to be less efficient and effective than buybacks. Now, of course, the government policies, as Tony outlined, are more than simply about recovering water. So this issue of whether an economic efficiency test is the only test we can debate, but I'm not really going to get into that very much. What I want to talk about is from the infrastructure side, how much water could be saved anyway? Is there enough lost water that we could solve all the problem by, lining canals or something like that? So that's the question I want to address today. And my key messages, I'll say up front, are going to be that there's considerable uncertainty in that number, how much water could be saved, but it's unlikely to make more than a modest contribution to the overall aspiration to return water to the environment. And following from those two key messages, I would say that we need a fairly careful accounting of savings required for investments insofar as those savings are, a principal objective of the investment. Okay, so I'm going to mostly look at infrastructure, by which I mean off-farm, but I'll also make some passing comments about potential savings on the farm. I'm going to look at the potential savings from a couple of angles. One, I'm going to look at a particular case study and sort of say, well, if we sort of add up from particular case studies and extrapolate across the basin, what does it look like? I'm also going to have another look at the alternative, which is sort of start with some gross figures across the basin and sort of partition up how much water it goes to productive use and how much is left over as lost water that might potentially be saved. But before I get to all of that, I want to have a quick look at some sort of process things. What really is lost water? How much out there is lost? So looking at losses, we need to focus on those losses which are true losses. So the first true loss is evaporation. So if we can stop things evaporating, canals, storages of one sort or another, that's water we could use for other purposes, be it irrigation or the environment. Some seepage and leakage losses from canals or other water holding bodies are true losses if they go somewhere which is of no use. So, for example, if they're adding to a salty groundwater store and we can stop that, that's water that would not be available for use, which we can then, by having stopped that loss, we can use. But some seepage and leakage is to fresh groundwater, which can be reused, and some, as in my little diagram in the top left, does flow down through the groundwater and return to a river or somewhere useful. And if that's not a true loss, if we somehow stop that loss by lining that canal with concrete or plastic or something, all we're doing is stopping water which is getting to a river or a useful bit of groundwater anyway. So it's not a true loss. We're not making a true saving by stopping it. In my diagram, the map there, the satellite picture taken from Google Earth, that's a little bit of the Murrumbidgee. So you can see there, that's the Murrumbidgee. This is Narrandera, Yanco's up there, and you can't see it very well, so I'll go to the next picture. I've outlined it in blue. That's the main canal taking off from the Murrumbidgee, which feeds the Murrumbidgee irrigation area. Now there we have a canal which for about 20 kilometres is never far from the river, and particularly up here returns to very close to the river again. Now that particular section of canal is one of the leakier canals in the Murrumbidgee irrigation area system. I'll show a little map about that in a moment or two. So we've got a leaky canal never far from the river. Where are those leaks likely to go? Some of them are likely to go back to the river. So that's an example of where there is likely to be a return flow to the river. However, I'm not aware of any study that really quantifies how much of the leaks are known, but how much of them get to the river, I'm not aware that that's known. However, if we were proposing to line that canal, I would say, well, we probably ought to know that. That's something we ought to be finding out. So true losses and potential savings. Evaporation is a true loss, and we can potentially recover that saving in several different ways. One is by piping canals. So there are sections of water delivery infrastructure, particularly in the very lower parts of the basin down in South Australia, where the pipes are used to deliver the water. There isn't really any evaporation from them. Indeed, leaks in general are very small from the pipe systems. We can also realign systems in such a way that the canal system is shorter, or at least has less surface area. We would save less water that way than with the pipes. We can manage canals a bit differently. In particular, canals, even when they leak, the leaks as a proportion of the overall delivery is less when we run canals full, so we're running them optimally. So we can save a little bit of leaks if we've got water reductions and we have to spread those water reductions across areas. It's better to spread them in a way which concentrates the use of canals running as fully as possible, because we'll be losing less water to leaks. Seepage leakage. Now, as I've just said, not all of that is a true loss. Much of it may not be. It can also be saved by piping canals, and again, you get the most saving that way. It can be saved by lining canals. Now, depending on the exact form of the lining, that's unlikely to be 100% effective. We can, again, recover water that way by realigning irrigation systems, and again, small savings are achievable through operations. As I outlined there, in general, the better the saving, the more expensive the option. But the main message I'm trying to get across here is that many of the savings measures, in fact, are not 100% effective. Now, going back to the return flows that I said a moment ago, just to put some sort of figures on this, there aren't many studies that I know of that really do a good job of quantifying how much of the water that's taken out of rivers and delivered along canals and ultimately onto the farm, how much of that in fact returns to somewhere useful. There are some back of the envelope sort of arm waving calculations about which suggest about 10%. So if you take 100 units, megalitres, whatever, out of a river, 10%, 10 of those units might come back. It varies in systems. Those systems which are already piped have virtually no return flow. Some other systems where the canals go across maybe fairly sandy soils may have much bigger return flows than that. Canal systems delivering water to farms are generally, across the country, across the MDB, something like 80% efficient. So of those 100 units, 80 make it to the farm, and there's some further losses, if you like, on the farm. Some of those losses, both on-farm and off-farm, are evaporation, and some are seepage or leakage downwards. Of that seepage and leakage, some is the return flow. The point I'm making here is that if we are looking to these parts of the losses to look for the water recovery, the savings, a considerable fraction of those losses are return flows. So a considerable fraction of the losses are not true savings. Now, I'm now going to turn to the first sort of a detailed study and look at how much savings there appear to be according to this detailed study, and sort of what would that be if it applied across the basin. I'm not saying it does apply across the basin, but it gives us a little feel to think about the numbers. And in the next slide, I'll talk about a sort of a more general top-down calculation. The Pratt study in the Murrumbidgee a few years ago, water saving study, suggested there was perhaps 300 gigalitres of water annually that could be saved in the Murrumbidgee. Now, the Murrumbidgee is something like a fifth of the water use. The water used in the Murrumbidgee for irrigation is something like a fifth of that used basin-wide. So just simple extrapolation, you might be thinking there would be something like 1,500 gigalitres of potential savings across the basin. However, if you really dive into the figures in that study, you find that it's not quite as simple or quite as optimistic as that. Firstly, part of the saving was from river evaporation. So if we're trying to save water to save rivers, well, presumably you want them to be there evaporating. So you're not really going to find much of a saving there. You can find some savings from other forms of river operation, but perhaps not great savings. 130 gigalitres of that 300 was from seepage and evaporation in the supply and storage systems of the MIA and the CIA. And according to this Pratt study, 42 gigalitres of that was seepage from a small fraction, about 20% of the overall canal system in the MIA. Now, there's a couple of things about that, and this, incidentally, is the map of the leakage in those different canals, and that's the section I referred to earlier from Narandra for several kilometres, where that's one of the leakiest parts of the system. Now, turning back to the figures, that 42 gigalitres is actually quite different from the Murrumbidgee Irrigation's own estimates of the whole system. So there's perhaps some question as to whether that seepage estimate is a bit high. And also, some of it, as I just outlined, is likely to be a return flow anyway, so it's not really lost. So that 130 gigalitres is probably not all there to be saved. The final 100 gigalitres is on farm, and again, there may be some potential savings on the farm. Just a point about on farm, some of the seepage downwards in the soil on farms is actually a requirement. If you just put irrigation water on soil forever and none of it ever leaks downwards, you accumulate salt because the plants remove the water but leave the salt behind. So you need a little bit of extra water to flush the salt downwards. So again, not all of that water is available to be saved. You have to have some of it moving on. And also some of it is a return flow anyway.